Thank you for having me. My name is Doug Zentz. I've been in ASHRAE for a long time. I'm what's called a distinguished lecturer in travel photographer ASHRAE. You're going to see one of my presentations that I do as part of that. This is on standard 189. It's a fairly new standard in ASHRAE. It's written in code language. And so away we go. The first slide really doesn't pertain to us because it's for normal EL presentations. So this standard 189, I see my slides got cut off. I want to talk a little bit about why we have this standard in ASHRAE, just a little bit. Why do we have it?
You want to have a quick look and see if we can fix that?
Yeah, sure. Because this standard's only been around since 2009. I don't understand why. I wasn't doing that on the first slide.
No.
Well, I don't think it's going to affect the meat of the presentation, so.
You think?
Yeah. We'll just roll with it. Because it hasn't changed.
Okay. It's probably be going from here to
That. Yeah. Okay. So I want to talk a little bit about why ASHRAE as a society has this standard. That'll work too. Then we're going to get into what is it? What is the meat of the standard? What's in it? I'm going to give you kind of the highlight film because it is a very thick standard. And then the last couple slides are kind of my suggestions on how you could use this standard. Okay. This is a topic that's been talked about for quite a long time. And I don't care if we're here in Greece or somewhere else in Europe or the United States or anywhere else in the world. If you think about where you were last night, you got up this morning, wherever you were consumed energy. You probably took a shower, warm water hopefully. Well, that took energy. You had to get here from wherever you slept, transportation, that took energy. You probably consumed some things, maybe toothpaste to brush your teeth or something, or you had something to eat. You're consuming energy. Every step along the way, we're all consuming energy. If you take what we all consume in energy on a daily basis, every day, and say, where can I classify that energy? Where's that energy coming from? How are we using it as humans? 99% of it can fall into one of these four categories. Either residential buildings, homes where we live, commercial buildings, transportation, that includes trains, planes, buses, everything, or manufacturing and industry. Notice if I take the top two quadrants, where we live, where we work, it's 40% of all the energy that's consumed by the human race. And the two bottom quadrants have been self-regulated and or have been regulated by governments for a long, long time. Governments around the world have been regulating transportation efficiency through CAFE standards of how many miles per gallon or how many liters per meter that you're consuming when you are using transportation. And industry tends to self-regulate itself because it goes right into their bottom pocket, their net earnings. If they're not efficient, they don't make money. The only area that really, for a long time in history, that has not been regulated or controlled is buildings. And this is becoming more and more aware of the fact that we do consume energy in buildings and that we need to start regulating it. Oh, by the way, buildings also represent this. 17% of all fresh water consumed, 25% of wood. I'm going to skip this one for a second. Waste generation. We generate a lot of waste out of buildings. And we're tired of probably new landfills and places to get rid of that waste. Natural gas and electrical use. This is your utilities. You can see that buildings consume the vast majority of what you would call utility energy, which is why buildings account for 1/3 of all of our CO2 emissions around the world. So buildings, directly or indirectly, are the largest consumer of a single thing of energy in the world, and also as a single thing are the highest production, directly and indirectly, of CO2 emissions. That has given life to a lot of new things, including this standard, which I'm going to talk about. But it's a continuing story. This is just two charts that represent basically the same thing. I don't care whose data you look at. I don't care what time and segment you look at. If you look at the next or the last 30 to 40 years, over here it's the green blocks, over there it's the red dots. Year by year by year, we are consuming more energy in buildings worldwide. Even though we try to make buildings more efficient, even though we try to make HVAC more efficient, lighting more efficient, we're consuming more energy. And there are reasons that are driving that. How many of you have at least one, if not more, devices that you plug in every day? Okay. 2, 3? Yeah, 3. That's what I figured. And when you travel, are you always fighting for a place to plug in? Mm-hmm. So we are consuming, and in the work environment, we're tending to push more and more people closer and closer together, because it's more efficient that way from a corporate standpoint, but it's creating more and more heat generation internally in buildings. So we have a problem. We keep consuming more energy. Well, where are we going to get the energy from? Where's the source energy coming from? Okay, now on the bottom of this chart, which I know is hard to read, that's 2010, that's 2020, that's 2030. So we're right in this segment right here. And even though we're putting in more renewable energy every year, the problem is we keep consuming more energy every year. And the growth rate of what we're consuming and the need for the base fuel for creating the energy we consume is outpacing the renewable energy that's being added right now, worldwide. And a lot of that is due to developing countries. Countries like China, India. They want to be like everybody else. When I give this talk in the States, I say that, hey, everybody wants the 3-bedroom home, 2-bath, garage, wants to drive down the street to the mall, place of restaurants to eat, go to the movies. Everybody wants that. It consumes energy to do all that. So we have a problem. On top of that, I'm sure all of you are aware of what the IPCC is, the International Panel for Climate Change. It's a part of the United Nations. They identified this years ago. Buildings are the low-hanging fruit, the biggest contributor as a single object to greenhouse gases through direct emissions at the building itself, because sometimes volatile organic compounds are a part of that in the buildings as they off-gas, but because the vast majority of the energy that goes to power that building around the world globally is still coming from a fossil fuel. And so we are literally pumping the atmosphere with CO2 based on our lifestyles, where we live, where we work. Okay? Well, now that I've probably scared you to death, I'm going to give you some bright news. In fact, I'm going to applaud the audience right now, because this started the chain reaction. Back in 2004, when the European Union started building energy labeling, this really started the wave of awareness around the world of the fact that, hey, we got to do something about buildings. Okay? How many here are familiar with the Building Energy Labeling Program? A few. Good, good, good. For those of you that aren't, real quick, this is a program that all the countries in the European Union back in 2004 all signed an agreement and said, yes, we will do this program, and whenever a new building was built or an old building was renovated or an addition was made to a building, the professionals involved in that building had to then create this document, which was then turned into a plaque for the building. But it essentially represents this. One column that says as built, that means the design of the building. So the architects, the engineers, the building owner got together and they modeled what is the building going to consume in energy down the road after it's built. And then the building is completed and is commissioned, and the owner takes ownership and they operate it, and they consume a year's worth of utility bills. And at that point in time, someone walks in, new career path person, certified building assessor, someone that can certify the actual footprint, energy footprint of that building by going back and looking at all the documentation. How was the building built? What are the commissioning reports? How's the sequence of operation look like? Really look at that in detail, but then also look at the utility bills and take all that electrical energy, all that natural gas energy, whatever utility they had, convert all that energy into one unit so that they can then report it. And I believe this is in kilojoules per square meter. So they report all that energy. And so you have one number that is what we think it's going to be when in the design, and then the real number. And then the owner, when they get this, then they have to create a plaque and put this at the front door of the building. So it's public knowledge. Everybody gets to see whether you have the good building, the bad building, or the average building. Okay? It's a metric. And they're trying to promote that awareness so people want to participate in making it a good building for energy footprint. Okay? And then in 2007, every country in the UN or the European Union wanted to start having their own version of it. Here's the Greek version. And how many in here are familiar with this right now today? Good, good. Well, that is what drove this. This is what's called ASHRAE's Building EQ program. It's starting in the States, but its roots are here. And so I say thank you. This program is gaining momentum. The Department of Energy in the United States is looking at this very hard. The last two acts of Congress that tried to pass in the United States of an Energy Act had this as part of it. It's going to happen. It's just a matter of when. But we are going to join the European Union with this system. So what is Standard 189? Well, Standard 189 really is looking at how do you develop a code language body of work that leads a path to the low building energy footprint, and do it in a way that's sustainable. So it's looking at elements of site development, water use, energy consumption of the building, indoor environmental quality, the materials for construction, and the actual construction process itself that leads up then to a sustainable operation for the building owner. That's what this standard is really all about. It also incorporates, if any of you are familiar with these three ASHRAE standards, ASHRAE Standard 55 on what is human comfort, how do we define it, how do we use it, implement it, what we do, standard 62.1, which is the version for indoor air quality or environmental quality, whichever way you want to phrase it, for commercial buildings. And then 90.1, which is the energy standard for commercial buildings. The thing that's different about standard 189 is it always refers back to the most current version of these three. That always is a big deal in the States because state by state in the United States has their own way of looking, well, I use this version or I use that version, kind of like the ICC, the International Construction Code. There are different versions that you could go by. Not always the most up to date. And it's also built on what's called the LEED Foundation. People know what LEED is, Leadership for Energy and Environmental Design. So this follows that format, okay? This standard came out in its first publication in 2009. It has been updated 3 times. This is what the standard looks like. It is a very thick standard. There's an awful lot to it. I am not going to cover everything. Don't have enough time to do all that. I'm just going to give you kind of the highlights here. There are several members that were involved in the sponsorship. United States Green Building Council and its array of members, which includes architects, engineers, and many other walks of life. There's the Illuminating Engineering Society. There was ASHRAE. And at the very end, and a very key part, was the International Code Council came in because they were at the same time developing the International Green Construction Code, the IGCC. And if you've seen the IGCC and or Standard 189, you will see that they now reflect and endorse each other. One says, if you follow the other one, you're good with me. And they both reciprocate. So they're coming together, closer together now with everything they do. Okay, so what is the intent? Well, this intent of this standard is much like the other ASHRAE standards. It's not intended for residential, it's intended for commercial buildings. Okay? So if you were thinking about the indoor environmental quality standard or the energy code standard from ASHRAE, this standard applies to the same type of building. And even though your area may not embrace this standard, this is an awareness of what is to come, what is the future in code standards and buildings, because this is gaining traction in many, many areas of the world. It is a standard, and its purpose is to have minimum requirements for site design, construction, and plans for operation. And that is the key words right there in this standard. The plans for operation. I'm going to talk about that at the tail end. This standard is different than every other standard out there because it embraces and recognizes that the building owner must operate the building. And how do we keep it sustainable 3rd year, 5th year, 10th year from what the intent was of the original team that designed and built the building? Okay? And it's also looking at a balance between all these things, looking at today and the future. It applies to what I just talked about here, new buildings and their needs, portions of buildings and their systems that are being updated and or added on to existing buildings. And it addresses the sustainable use of water, efficiency, indoor environmental quality, the building's impact on atmosphere, materials, and resources. So it's an all-encompassing standard that looks at buildings holistically. If you're familiar with LEED, this contents of this table here should look very much like LEED, except for the plans of operation. That's the thing that makes it different. So the basic structure in this standard is like a lot of other standards. In each section, they're going to give you a scope. What is this area about? Then it gives you compliance. What do you have to do to be compliant? Followed by what are the mandatory things you have to do, which makes it different than LEED. In LEED, they give you a choice laundry list of things you can do. You don't have to do everything. In this standard, in every section, there are mandatory things you must do. And then there's option 1 and option 2. Option 1 is a prescriptive area that says if you do these things, follow the bouncing ball, you'll be in compliance. If for some reason you want to have your own design, you can do option 2, which is performance-based. And it tells you how to meet the standard if you do the right performance procedures in those areas, whether it's water efficiency or energy efficiency or indoor environmental quality. Okay? So you can do either one of these. I'm not really going to talk much about option 2 because I don't have enough time. I'm going to strictly look at mandatory and prescriptive in most areas. I'm going to start out with Chapter 5 on sustainable sites. And the first thing in the mandatory area is they want to reduce the locale of the building so that we're reducing the island effect of heat. So in this area, there are certain things that they tell you you must do on the site around the building, and also the shading. They want you to have in the sides of the building that are going to be hitting direct sunlight. First 20 feet up, they want green growth for shading on the building. So now you got to figure out, okay, on the east, southwest, I have to put in vegetation. I got to water the vegetation. I don't want it to die. And I got to integrate that into the building and the site. And there's also some requirements on the roof in many areas that has to do with the reflection of a solar load off of the building. For those of you that love acronyms, because our industry doesn't have enough of them, on light pollution, I love this one. We want to limit the amount of bug, backlight, uplight, glare. We spend a lot of energy for nighttime lights. We don't want the astronauts taking advantage of that. We want to keep that light down on the surface. So it's all about using the right type of lighting to light up the building. And the other lighting standards in this standard are much more stringent than 90.1. In fact, that is a blanket statement. Everything here is more stringent than the other standards. In water use, I love this slide because it's just so typical of what I see. You have to use smart irrigation controls. You have to use high efficiency water systems and water devices. Let's just call it that. Okay, whether it's a hydro system for plantation, or whether it's a water closet or anything else in your building, you have to use smart type devices that manage your water. Your plumbing fixtures have to have governmental standards in your part of the world that say that yes, these are low water consumption devices. And in the United States, that would be US Energy Star rated. But you also have to do a lot of metering. Any building that is more than this in water consumption per day, total water consumption a day, must have metered water. What are you using? And keeping track of that. If you have systems that consume water, G, and HVAC, do we have systems that consume water? Yes, we do. So there are thresholds built into the standard based on the type of equipment. There are tables. So if you have cooling towers or other devices that are consuming water, like boilers, you have makeup water to these devices. You have to meter that makeup water. You also have to meter the water that you're using for flushing the systems. You're flushing down your cooling towers or your boilers. You have to meter that. How much water are you using? And then here's another one. If you have air conditioning equipment that's going to dehumidify the air, If you're in certain climate zones where your mean wet bulb is above that range, you have to collect condensate off your cooling coils for any unit that's bigger than this threshold. And that's not that big. So you have to collect that condensate and then have a water harvesting system where you're going to reuse that in either irrigation or back to your water closets. Here's an example of some of the tables. You can see for different types of water, if your consumption is over these limits, you got to measure it. And then in certain specific applications, again, if you're over these thresholds, you have to meter your water consumption and water use. And we'll talk about meters and what kind of meters there are when we get into the energy side. Speaking of which, here we are. Now, the highlights of Chapter 7, which is the big chapter on energy consumption. In that chapter, the main goal is to try to always be 30% better than whatever the last energy standard was. This is always setting the bar 30% better, which is a big step. It's a real big step. If you're familiar with Appendix G in 90.1, that is, how do I create what's called a baseline model for my energy consumption of my type of building? There is a similar appendix, it's called a normative appendix in this standard, which sets up the same reference. You can model what a standard building would be and then look at your performance of your building against that standard. They also want you to do what's called peak load reduction. And they make a flat statement. They want you to reduce your load by X%. It's up to you how you do it. For those of you that saw the presentation earlier about load shift, well, that's one way you could do it. There's other ways you could do it by maybe widening your dead bands and illustrating through modeling that you widen your dead bands, you're reducing your peak load. However you do it, it's up to you. But they want you to do it. And then there's many other areas which are much more stringent than 90.1. So the first thing in the mandatory requirements on site is they want you to have provisions for on-site renewable energy installation. You don't have to put it in yet, but you have to have the provisions to put it in, which means you got to have a dedicated roof area or dedicated other areas adjacent to the building to put in renewable energy. There are a few exceptions. I don't think you're in a low incident solar region here, so that probably wouldn't apply, but in some areas people can purchase what's called green power. And that is your check mark for getting off the hook if you're going to buy green power. Other mandatory requirements are your metering. All meters have to be either automated reading or remote with data, the ability to record the data, and preferably they want it communicating with a central recording system, and they want to see 36 months worth of data. So all metering has got to have 3 years worth of data collection, ongoing. Specific items have to be metered. Your on-site electrical source, and then also any specialized, like in the HVAC world, any device that's more than 100 kVA. There's a lot of things that are more than 100 kVA. If you've got a big building with big chillers, chances are your big chillers are more than 100 kVA. So there are many things that have to be metered. People moving systems, lighting systems, so they have to have their own independent metering. Okay, those are the mandatory things you have to do. Now we're going to get into the prescriptive elements in energy. We have to, well, if we want to follow the prescriptive path, we got to do these things. And if we do, we comply. Or I'll show you the tidbit of the performance path, because I think it's kind of interesting. The first thing in the prescriptive path in renewable energy says, okay, you provided the means of on-site energy generation, now go do it. Put in the solar panels, put in the on-site renewable energy so that we are now in compliance. Again, exceptions. The low incident solar regions And then if you're buying green power, you don't have to do it. But if you did provide a means for putting it in, now they're saying put it in. How many are familiar with the tables in 90.1 on the U values and the solar heat gain coefficients and all the wonderful tables that are in that energy standard? Well, they're also in this standard, but they're more stringent. So what happens is your walls, your windows, everything becomes higher quality. And I don't know about what it is here, but I know in the States, when I talk to engineers, how many are practicing engineers in the crowd? Okay. Whenever I talk to practicing engineers, and we talk about what are your typical design standards? What do you design to? And I get engineers all the time that tell me, well, I designed a code. I designed a code. And I say, congratulations. You designed a code. That means you're designing the worst building you can legally get away with.
It depends on the code.
I understand that.
Still, it's the minimum.
It's the minimum. Typically, almost 99% of the time,
Yes.
you can do better.
Yes.
Okay? Also for fenestration, in this standard they want you to have overhangs, and there's a relationship there of the overhang and the window height they want you to follow. They also want you to have an orientation on your building where your east-west is less than your north-south in exposure of fenestration, so that we're not increasing our solar component on the building. And these are mandatory in climate zones 1 through 5. And I have to apologize, I tried looking up to see what the climate zone number was for here, and I couldn't find it. Could you tell me what it is?
Say again, sorry?
Your climate zone number, ASHRAE climate zone number for this area.
I think
Is it
eight.
2?
Mhm.
3A?
I think it's 3A.
3A? Okay.
think it's 3A.
Okay, I could, well, it's definitely in the 1 to 5 range.
It's not 2, it's 3A, I think.
Okay, but that's still in the 1 to 5 range, because it's a 3. The difference between A and B is it has to do with something different. It's still in where it would be applicable, okay? And that's because of the sun, and where it is in relationship to the equator. So you would still follow this. Now, they do give you an out here on the projections, the size of the projections. Because if you got higher quality glass, and or if you do the opposite, you put in more projection, you can use lower quality glass because you don't have as much solar direct on the glass. So they give you a table here that basically says, okay, if your overhang is bigger, more overhang, then you can use lower performance solar heat gain factor glass because it's going to be shaded most of the time, which is a nice credit. Demand controlled ventilation. Who does demand controlled ventilation? Anybody? Okay, well, it's a good thing, and especially a really good thing here because in this standard, they not only give you benchmarks for sensing, and they also give you some descriptions about the sensors that you're going to use, you know, and their accuracy and the suggested maintenance of when they need to be looked at periodically. But they also give you some nice things down here. And what I mean by that is they go beyond standard 62 in giving you a lower baseline for people, density factors. So you can actually get the demand controlled ventilation to work. You set the standard lower, and then you let the demand controlled ventilation work. So you're only using the minimum amount of air when there's really nobody there. So you lower the threshold and be able to actually use that demand controlled ventilation working process. Okay? So you get lower design assumptions, basically what it means. Okay? Economizer use, outside air economizer. I don't know, do you guys use outside air economizer here that much?
There's not a big rooftop installation base here in Greece.
Okay.
But that being said, some of the engineers we work with, I would say the past 5 years, they're starting to take that into consideration simply because
Okay.
it's there. So, but
Okay.
again, there's a little thing between how much you can economize in the minimum
Right.
regulation.
I understand that, and that's why I asked the question, because I wasn't sure. Okay? But if you do use outside your economizers, they want you to have a lower threshold as to when you're actually going to start to use them. They want you to go down all the way almost, basically to 3 tons of cooling, which is pretty low. And if you're doing VAV, variable air volume, they want you to do supply air reset. Max, or I should say minimum of 5 degrees.
No VAV,
No VAV?
not very.
Oh, okay. Big in the States.
It's huge.
Yeah, yeah. Okay, so I'll just kind of blow by the top one then, since we're not using VAV. This right here, how many of you are familiar with what's called the fan power limits and brake horsepower per ASHRAE 90.1 when it comes to your air handling units? It's a relationship of your airflow and then your static pressure. Okay, well, there are thresholds that are 10% more stringent. And when you follow this standard, what it means is this: to meet these goals, you generally have to oversize your air handlers, because you have to slow the air down in the air handler itself and drop the static pressure requirements so that the brake horsepower requirement for the fan goes down. That's the only way you can meet it. Air handling manufacturers probably love it.
Which
But
the key concept, if I may, here is that people have to understand that this is an initial higher capital cost,
right?
but at the end of the day, the
Your-
ownership costs
Oh yeah,
tremendously lower.
tremendously. The payback on it's actually pretty fast,
Yeah, very fast.
because with those air handlers in many buildings, like this building's a good example, those air handlers probably run all the time. So that's a year-round operational savings. So the savings happens pretty fast.
Yes, but, excuse me, you are talking about only the internal static pressure on the drop, or the external in the ductwork as well?
Well, the ductwork is up to the design. I can't control that, but I'm talking about the internal. The external does count because it's looking at the brake horsepower consumption of the fan. So if you have high external static pressure requirements, then this becomes a real big problem.
Yes.
Because now you're trying to compensate for, how should I say, extra ductwork requirements. And so you have to make the air handlers even more efficient, which is difficult, especially if you have high filtration needs and you're going through higher quality filters. If you increase the MERV rating on the filters, your air pressure drops tend to grow. So this is a big deal. When I talk to engineers, this is one of the biggest sticking points with this standard, is keeping the brake horsepower limitations down on the air handlers. This is also coupled with that. And this has, well, it does have something to do with the standard. You said you're 3A, okay? If you're 3A, you're right here. This says if you've got just, let's say you've got 12% outside air, not real big, 12%. It means that you have to have energy recovery on your air handlers if you're over 30,000 CFM. Now I'd have to do math in my head here. What would that be in cubic meters?
1.7, I think. 1.7 divided by 1.7.
Yeah, so
say
about
15,
13,000,
13.
about 13,000 cubic meters.
Wow.
I mean, this is not a huge air handler, but this means you got to do energy recovery. And the caveat is this: it's got to be 60% energy recovery efficient. So what kind of device is that can get to 60% energy recovery effectiveness? There's only one that I know of, and that's an enthalpy.
That's what
Yeah.
So now you're into enthalpy wheels being added to your air handlers once you hit that threshold.
There might be some, I don't know if there are, I'll speak for a manufacturer, I should know this detail, but I think they're getting up there having some cross-flow heat
Yep.
exchangers.
Those are sensible only typically.
Well, yeah, exactly, but they have, I know we have some, I don't know the efficiencies of that actually, they're not applicable, for example, when you have exhaust air from washrooms or kitchens.
Well, that's process load.
Yeah.
Yeah.
They're getting, I don't know if they're that high, but, and again, parenthesis, this is taking into consideration that you have return airflow to the air handling unit, because if it's 100%.
Well, you got to have some form of airflow coming to it, exhaust, return, something. Yeah. Which is another thing to think about.
Yeah.
Yes, this gets more complex.
The problem is that you cannot always use the exhaust air.
I know,
It's a
because
big problem.
it's different class air and you can't cross-contaminate. I understand that. Hey, the standard is just saying they want you to be conscious about energy recovery. If you can't get to 60%, you got to use a different tile because of cross-contamination class 3 air, class 1 air, you can't cross-contaminate. I understand that. It might have to happen. Maybe the best you can get is 48%. And you go, hey, it's the best we can do. Peak load reduction. In this chapter they say, prove to us, and here's where that normative chapter comes in, where you model the base building and then you model your design and you show that because of your thoughts, deadband control, thermal storage, however you're planning to do it, CHP, combined heat and power, I don't care how you're going to do it, show me how you're going to reduce, the building peak by 10% of the demands of the system. Okay? They want you to document that. They also have additional lighting density factors that you can take advantage of. They want you to lower your lighting levels in the building. So when you start applying these additional factors to your other factors from the electrical lighting side on the energy, you're reducing your overall internal lighting power. This is driving you more and more towards LED lighting in buildings, which is really a good thing, because it also lowers our cooling load. Also in the lighting section, they want you to have occupancy sensors in areas that are rarely occupied, like hallways, storage areas, transfer areas. They want you to have lighting levels there where you can actually reduce the power even more when people aren't there. And then egress lighting, they have some thresholds there for egress lighting, and also auto controls for natural lighting integration. So if you put in natural lighting windows, especially if you have horizontal windows or ceiling windows, and you're trying to integrate the use of those windows as part of your lighting scheme, they want you to have your man-made lighting, dimming control or staging control, so that you're mirroring the two lighting systems together. Okay, those are the elements, or most of the elements, from the energy prescriptive side. If you don't want to do those things, you can now do the performance side. And the performance side of the energy chapter in Standard 189 basically says, okay, we're going to demonstrate that we use less energy than the base building. And we're also going to, in that demonstration, we're going to show that we're also saving carbon dioxide emissions. Now this is the interesting part, because once we get into this path and we do the energy modeling to perform all that and show that that's happening, they want you then to take your energy modeling output and they want you then to create a carbon footprint for your building. This is the first place I've ever seen in a standard where they're promoting the idea of you calculating the carbon footprint for the building. Now think about that. You have building energy labeling already in existence in the European Union. Down the road it's going to be in the United States. It's going around the world. The next step is this, carbon indexing at the building level. What's the next step beyond that? Can you say taxation of carbon indexing at the building level by governments?
No, we have enough taxes here. Please don't.
It applies, in theory it applies.
I know.
In practice, no.
In practice, no. In theory, yes. Down the road, could it? Maybe. When I say this in the States, everybody fringes, just freaks out. But I think it's going to happen at some point. Maybe not in my lifetime, but I think it's going to happen. And then if we go back to source energy, that's a whole nother kettle of fish. Start talking about source energy benchmarking or source energy use, because that gets really messy. Okay, indoor environmental quality. And I love this photo to represent indoor environmental quality, because we are really talking about what is good for us, what's healthy for humans, and embracing that we should be looking at that as a part of our code standards, not just how much air do I bring in outside and what kind of filters do I use, but what's really healthy for humans in buildings, because we spend a lot of time in buildings. And so we should really be looking at the total picture here, which is not only just your outdoor airflow, but it's also smoke control, it's indoor monitoring of the air, and it's really looking at the cleaning effects of the air in the building, okay? We'll start that out by saying, okay, I'm probably going to go over. I'll try to go as fast as I can. No smoking, that should be self-explanatory. Also, standard standard 55. Everybody should be familiar with that about what is acceptable indoor treatment of the air so that we're comfortable, what makes us happy. This is something that's new, and basically what it comes down to is this. At your entry points in the building, you have to have a system in place for people to wipe their feet, so that we're not dragging debris and dirt into the building that now we have to deal with in the cleaning process and the indoor environmental quality. So they want you to have a human factor so for people to wipe their feet. By the way, do you ever go around and, well, we don't have the kind of diffusers in here. Well, we've got some slot diffusers over there. Do you guys ever stare at the diffusers in buildings and you see the black streaks that come out of the diffusers? What's the first thing you think of when you see that?
No maintenance.
No maintenance where?
In the ductwork.
In the ductwork?
Yes.
Filters, air handlers? That's the wrong answer.
Plus pollution in the air inside.
I understand that, but the pollution didn't come from the air handlers and the ductwork and the system. They came from your feet. You walked in here, and the dirt came off of you and us and me, and then if maintenance isn't cleaning the floors properly, are you familiar with what's called the Coanda effect of the air coming out of a diffuser? It's a simple relationship of Bernoulli's relationship of velocity and pressure of fluids. If I have high velocity, I have low pressure. So the air coming out of the diffuser is whipping along the ceiling right there, much faster than the air around us. It creates a low pressure zone. Down here where the dirt is, it's higher pressure. The dirt migrates its way up and collects at that low pressure zone. And then if it's like a lot of buildings, you have corrugated ceiling tiles that are nice materials to grab dirt as it whips by. And so whenever you see diffusers like that, you need to tell the building owner, you need to clean the floors. True story. This shows you that, hey, if you want to put in natural daylighting, these are some guidelines that say you must do overhead lighting if you have certain types of spaces. It's usually large open areas with higher ceilings. You have to put in so much natural lighting to represent a reduction in your overall man-made lighting. This also gives you some side lighting guidelines for bringing in side lighting that's up here so it reflects upward and helps to create natural lighting in the spaces. There's also shading the exterior of the building and what they, guidelines of what they want you to do there, again, to reduce the solar amount of lighting coming through the building. And volatile organic compounds. They want you to use elements within the building that reduce your VOC content in the building. How many of you have ever bought a brand new car? And you get in it the first time and you go, I like that new smell. You know that's a volatile organic compound, don't you? Okay. That's emissions from all this nasty stuff. They want us to reduce that in buildings.
So it's better to have an old car.
Yes! Okay, so construction waste. There's a plan in there, much like LEED, for you on how to reduce, recycle, and limit your stuff. Also, collection points for the owner to set up collection of recyclables, and also discarding of ballasts and fluorescent lamps. Building acceptance testing. Okay, some people might call this commissioning. It's more than commissioning. And in this standard, you're saying basically this needs to start earlier. This needs to start in the design process. And it goes and continues. And it's looking at everything, not just what you might have a commissioning contractor look at. It's involving everything in the building. And if you're going to do commissioning, and they want you to do full commissioning on anything that's over 5,000 square foot, which would be what, about 2,000 square meters? About? Okay? They want you to have your commissioning process including all these things, which is a lot more than most people do. They also want the commissioning agent involved at various steps of the design phase, because those people have input, good ideas that will make the process easier down the road. They want you to have a good developed plan for site erosion, and I love that picture. Make sure that you implement that properly at your site. You can tell I have a sense of humor. Yeah. They want you, to have a plan for not only construction, but how are you going to use things during construction? You cannot use your air HVAC equipment during the construction phases and get them all plugged up with junk from construction. They want you to have temporary units if you have to have temporary units. Don't use the new stuff. Okay? Okay. I'll be quick here. I'm almost getting there. Here, this is a table, first time I've ever seen this. We talk about VOCs and new car smell. When you do your commissioning, they want you to do a burnout to burn these things out of the building. If you don't know what that is, basically elevate the temperature of the air, ventilate it for so many hours, and try to get all that out of the building. And these are acceptable limits then for testing afterwards to make sure you're underneath the thresholds. Site sustainability, if you're going to put all the money to put all the vegetation in, we got to have a plan to keep it alive. So they want you to illustrate that, basically. And you got to go through a measurement and verification process on your water systems to make sure you're using water efficiently, document it. Same thing with your energy management system in the building, and your management system has to be able to track energy and assess it and report it with various different reporting mechanisms. It's very specific. We also have to have a lot of documentation to make sure we're following the proper footsteps for indoor environmental control with our air handling systems, with the burn off of the VOCs, and then a plan for the owner to continue that process down the road. And they want you to use a cited standard 180 for a maintenance plan and the proper documentation, again, for the owner to set up sustainable usage after you leave the project. This is the first place I've ever seen this. It probably doesn't affect you as much here as it does us in the States. This is the first place I've ever seen that when somebody says, hey, do a life cycle study. Well, what does that mean? How many years? This is the first place I've ever seen that says for most commercial buildings that should be 50 years. Because most commercial buildings are built to last that long.
In our legislation as well.
Good.
Yes.
Good.
In
It
theory.
stays.
In theory.
Yeah, in theory. Yeah, I understand.
Not mandatory.
Τώρα υπάρχει. Cost optimal.
I want to share with you 3 last things before I leave. My suggestions on how you can use this, taking advantage of this standard, and then I like to end with what I call the pyramid. Okay, my suggestions. If you're going to use this and or you're going to be involved in the project of 189 or the International Green Code, then you got to get buy-in from the team. The team is everybody involved with that building. It has to be a team approach. It's the only way it's going to get done. Early decisions make big influences on everybody else down the road. Look at the building orientation, the exterior features, and the site requirements. That starts early, and once you set that, you can't change it. Okay? And then, this is really big, and this is something that I preach and preach on in the States. We don't do this as an ASHRAE society and as engineers. We typically don't do this. Think about this. When this building was a concept, idea, this room had a purpose. Just like every other room had a purpose. All the decisions that were made by the engineer to design the HVAC system, the lighting systems, any system for this space, were built off what was the purpose for this space. Do building owners change their purpose in their spaces after we're done? Do they understand that they may have to revisit the HVAC, the lighting, and everything else that supports that space? No, they don't. What we need to develop, and I call it the BOP, the Building Operating Plan, we need to create a roadmap that starts from what is the purpose of this space, that then follows by here's the design and why to support the purpose, followed by the system description, followed by the commissioning reports, followed by the energy management controls and the temperature control system and automation system in the building. And everything needs to be tied together so that the building owner knows if they change the purpose of the space, they need to revisit all those things for sustainable operation. We need to tie it together for the owner. Firms that understand this and do it, added value to the owner. Added value to the owner. This standard basically gives you the tools to analyze the best for the building through all these various things. If you embrace what I've said, and I haven't said everything, I kind of wet the whistle, then you can get in there and you can show the owner value. Because this is what I mean by the pyramid. If I take the true life cost of the building over the true life of the building, first cost is the smallest piece. The next piece is maintenance, the largest piece is operation. What will we do that's really bad in this industry? We tend to focus too much on this.
Yes, because the last one is not paid always by the...
I understand that. And people don't think about what the true life of the building is. With that, thank you for your patience. I hope you got something out of it. Any questions?
Actually, I have two questions if no one else has.
Okay, we'll make them easy.
No.
Όχι, πρώτα έχω κάτι. Somewhere you mentioned that in order to be compliant with the standard, regarding the plumbing equipment, for example, you have to use equipment that is certified by US EPA or
Well, that was
similar stuff. Okay.
basically, and they mirror the IGCC. So whatever you use in Europe that is of the higher quality plumbing
That's
fixtures.
the question. I mean, not always to plumbing equipment, to
Right.
any sort of equipment.
Right.
If I want to implement the standard, for example, in India or in Greece, maybe it's not easy to use something that has certification by US EPA.
Right, and there's where you could go back to
You
the
have relevance.
international code.
Okay.
You could go back to the IGCC.
Yes. That's the one. This is one question. The other is something we had discussed earlier with regarding the heat recovery
Yep.
efficiency.
Yep.
there is a trend to increase the threshold for the efficiency in heat recovery. For example, we discussed about the 60%,
Yep.
which is not something easy to have. Okay.
Correct.
Is there any effort in the technology towards the years to come to be able to mix different classes of air mixtures? For example, have the air extracted from the big hoods in the big kitchen, which is something, for example, 40,000
Yep. I know where you're going with this.
per hour. Why to lose this energy?
Well, there are ways in which you can recover that.
Mm.
It's not as efficient as what I was talking about, but if you partnered that with something else, where you could show them the net effect of two things together, got you to that. That's part of the performance-based option 2. You can do that. If you could model it and prove it, show it. Like in the kitchen exhaust area. Well, do you know what a runaround coil heat recovery system is? You can do that in the kitchen exhaust.
You will go where to water and then
Yeah.
water to where?
Yep,
Okay.
yep. You could, that's part of it, and then you could do something else, you know, in combination with that, and maybe get to the same energy that you need.
I've implemented that at a pharmaceutical plant where the
Yep.
exhaust fumes are very high temperature.
Yep.
With glycol runaround movement.
Yep.
It's actually effective, but the costs are high.
Yeah, the first cost is high.
Yes. Yes, but it's a big amount of energy. That
Yep.
it
Yes,
goes
it
lost
is.
in many cases.
Yep. Did I answer your question?
Yes.
Good. Any other questions?
I have one quick one. You said it in the beginning, just out of curiosity. You showed certification of a building, design as built B,
Mm-hmm.
as is in use D.
Yeah.
Now my question to you is, in your experience, what is the main reason for that? Is it design flaws? Is it construction flaws?
Oh,
That's a big difference.
There are so many things that you could point to. Based on my experience, there's one big area. How many of you do energy modeling? Anybody? 1, 2. What do you use in your energy modeling for what I call plug load? Where you're plugging something into the wall that consumes energy. Do you have a rule of thumb?
We have a rule of thumb, but we have also standards.
I understand
I
that.
either use the standard or I meter
occupancy
it.
of-
or
Okay, so
I
you use
meter it.
you use either your own documentation internally or you reference a document.
Or I meter it.
Or you meter it, but it's,
Yeah.
if you're doing a plan, something that's new, how do you do that?
You don't know.
You
You
can't.
go to the standard.
Go to the standard, okay. I'm gonna tell you right now through experience I know in the States. If you're going to a standard or you're going to an internal rule of thumb, you're off by a factor of 2. Okay? Plug load account, from what I've seen in real buildings, plug load accounts for somewhere between 15 and 20% of the building load. 20% is a big number.
Regardless of the use of the building,
Yes.
this figure.
Well, I'm giving you typical numbers, round, you know, I mean, it varies. What we tend to do in our industry is underestimate plug load. And so that answers your question typically from what I see. Hey, we're supposed to be a B building, why is that a D building? Well, that's because think about your buildings you walk into and everything that's plugged in. When everyone leaves, do they turn all those things off? Typically, no. They're running. It's called parasitic load. Parasitic load is very high, typically, in most buildings.
So false, they poop in, poop out, kind of false,
Yeah.
false data.
Okay, answer this. When you walk around your house at night, how many little things are glowing?
Standby.
If you have the new flat TVs, you know, certain brands consume almost 40% of the energy even when it's off, if it's plugged in. So there's a lot of parasitic load out there. That answers part of the problem. Well, I don't want to stand between you and lunch.
Thank you very much.
Thank you very much.
Thank you.